Good evening, friends. Welcome to day 9 of the Six Sigma Masterclass at 8 sessions. So, we were discussing about testing of hypothesis, which is a very important concept under the analyze phase. So, testing of hypothesis will be performed in order to validate the significance of the vital few causes with respect to the business problem. And testing of hypothesis is a tool which would help us to analyze the sample data and make an inference about a population characteristic. So in testing of hypothesis, we will have couple of hypothesis statements framed at the beginning of the exercise. One is called the null hypothesis, which will be denoted by H naught. And the characteristic of null hypothesis is that it will always take status quo or equal to position, whereas the challenging statement for the null hypothesis, which needs to be proved, is the alternate hypothesis, which will be denoted by HA. Then, as I told you, if you have the entire population data with you, then there is no need for us to perform testing of hypothesis because in hypothesis testing, we make an assumption about a population metric or population characteristic and then validate whether our assumption is correct or not. And then in hypothesis testing, all the decisions will be taken from the null hypothesis perspective. We will either accept or reject the null hypothesis. If you happen to reject the null hypothesis, then there is no other option but to accept the alternate hypothesis. And then we also looked at some three scenarios and learned how to frame the hypothesis statements for all those three scenarios. And then we also understood about the sampling errors that can creep in when we perform this testing of hypothesis exercise. So, a couple of sampling errors associated with hypothesis testing. One is the alpha error or the type 1 error, which is about rejecting the null hypothesis when it is true. And the other one is the beta error or the type 2 error, which is about accepting the null hypothesis when it is false. But then these sampling errors, when it is extended to a manufacturing scenario, the alpha error will be referred as producer risk, which is about rejecting a good lot. And then beta error is called as consumer risk, which is about accepting a bad lot. And then we also looked at a couple of important terminologies called confidence level and confidence interval. This confidence interval is also called as margin of error. So when we deal with sample data and make an inference about the entire population, we cannot be 100% confident about the population result. So when can we be 100% confident about the population result? Only when we are measuring each and every unit in the population, right? So when we are dealing with sample data and making an inference about the population, we can either be 90% confident or 95% confident or even 99% confident, right? And we can also assign our own confidence levels. We can also assign 94% confidence or 97% confidence, right? So these are the generic confidence levels that we would assign for a hypothesis testing exercise. So when I say that the confidence level is 90%, what does this indicate? So it indicates that we are 90% confident that the null hypothesis statement is valid and 10% chances are there that the null hypothesis statement could be invalid and we might end up accepting the alternate hypothesis. But then as I told you, if nothing specific is mentioned about the confidence level, we need to consider the default confidence level to be 95%. So 95% confidence level, we will be 95% confident that the null hypothesis statement is valid and 5% chances are there that the null hypothesis could be invalid and we might end up accepting the alternate hypothesis. Similarly, 99% confidence level would indicate that 99% we are confident that the null hypothesis statement is valid and 1% chance is there that the null hypothesis could be invalid and we might end up accepting the alternate hypothesis. But then we need to look at both confidence level and confidence interval or margin of error together. So what is confidence interval or margin of error? Again, when we deal with sample data and make an inference about the entire population, We cannot come up with a point estimate about the population result. We can only come up with an interval estimate. And this interval estimate will be derived from the sample metric that we would have calculated, right? And one thing that we could clearly understand here is the interval estimates will become much more wider when we increase the confidence level. So as the confidence level increases, the width of the confidence interval will also become much more wider. And towards the end of the session last Friday, we looked at the sample and population notations for the various statistical matrices. So for mean, we have the sample notation x bar, and the population notation will be represented by mu. And then variance, the sample notation will be small s square, and the population notation will be sigma square. Then standard deviation, the sample notation will be small s and the population notation will be sigma. Again, sigma and sigma level are two contradicting matrices. So sigma would denote the population standard deviation, whereas sigma level would denote the quality or the efficiency level of a process. And as we already seen, when we are able to reduce the standard deviation, we will be able to increase the sigma level. So both are contradicting matrices. And then we have proportion, which is the primary metric for a binary discrete data. So the sample proportion will be denoted by small p and the population proportion by capital P. And then the average for a count discrete data. So the sample average will be denoted by small lambda and the population average will be denoted by big lambda. And finally, the size. So the sample size will be denoted by small n and the population size will be denoted by capital N, right? So today we are going to continue with our discussions regarding hypothesis testing and also the other concepts that are part of the analyze phase. And then we will have the training session for the first 3 hours. And the final 30 minutes, you'll be taking the mock test for the Greenbelt assessment. So as I told you last week, those who are directly enrolled for the Black Belt certification program, so they will not be able to take the mock test and the final assessment for the Green Belt certification, that is today and tomorrow. So they will directly attempt the mock test for the Black Belt assessment on Wednesday, that is on 21st. Yeah, 21st. And then they will take the Black Belt final assessment on the final day, that is 22nd, this Thursday, right? So those who are enrolled for both Green Belt and Black Belt certification programs, they will be eligible to attempt the Green Belt mock test today, the final 30 minutes, and then they will also be able to take the Green Belt final assessment tomorrow, right? Fine. So I hope you all have checked your dashboard and have found out whether you have been enrolled for both Green Belt and Black Belt certifications, or you have got an exemption from appearing in the Green Belt assessments and you are directly enrolled for the Black Belt certification. Right. So let me just share my screen. So next we are going to look at the list of hypothesis tests that we have for the various statistical matrices. So I've given this in a table format because in the final assessments, we will not get any exercises pertaining to hypothesis testing as questions, right? So you'll not get any exercises pertaining to hypothesis testing as questions in the final assessment. So you'll be given a scenario and you'll be asked to identify the appropriate hypothesis test logic that you would apply for solving that case scenario, right? So hence you need to be familiar with the scenarios pertaining to all these hypothesis tests, right? So that's why I created this in a table format wherein we will have the statistical metric in the first column and then the hypothesis tests that can be performed for that statistical metric will be in the next column. And in the final column, I have also given the scenario so that you can clearly identify given a scenario which hypothesis test you need to deploy for solving that case scenario, right? So let us look at the list of hypothesis tests in detail. So first we are going to look at the hypothesis tests that we can deploy for mean as a statistical metric. So mean as a statistical metric, we all know, can be applied only if the data distribution is normal and random. So if the data distribution is non-normal and non-random, then we need to apply the statistical metric called median, right? So we all know that. So mean as a statistical metric for normal and random data set. And we have four hypothesis tests under mean. So what are these four hypothesis tests? So the first one is one sample Z or T test, and then two sample Z or T test. Then we have pair T test, and finally we have ANOVA under mean. ANOVA, the full form is analysis of variance. So even though it is titled as analysis of variance, this is actually a mean test, right? So we'll find out how it is a mean test when we actually solve an exercise under ANOVA on the 11th day of this training session. Right. So now let us look at all these hypothesis tests in detail. The first one is one sample Z or T test. So this is one sample mean test, right? So when we have one sample mean test to be deployed, then we will be referring to a scenario wherein the samples will be drawn from a single population category, and we would want to validate whether the population mean of that category is equal to some target value. So the scenario will be the samples will be drawn from a single population category, and we will try to validate whether the population mean of that category is equal to some target value, right? So this is the scenario for which we will apply one sample mean test. So we have couple of tests there, Z test and T test. So when to apply Z test and when to apply T test, we will see in a short while. But before that, let me give you an example for the scenario. Say there is a bike manufacturer who has come up with a new brand of motorcycle. So he claims that his new brand of motorcycle can give a mean mileage in excess of 50 kilometers per liter, right? So the bike manufacturer says that his new brand of motorcycle can give a mean mileage of more than 50 kilometers per liter. So if you want to validate his claim, then we need to perform this one sample mean test, right? So here, what we would do, so we will pick some few sample motorbikes, pertaining to that new brand, and then test it out, and then validate and find out what is the sample mean mileage provided by those bikes. And then with that sample mean mileage data, so we will try to validate whether the population mean is exceeding 50 kilometers per liter or not, right? So here we are drawing samples from a single population category. So what is that single population category? The new brand of motorcycle. So it could be brand A or whatever. So the single population category is brand A, right? So we are going to draw samples only from that category, and we are validating whether the mean mileage, the population mean mileage provided by this new brand of motorcycle is exceeding 50 kilometers per liter or not, right? So we are actually validating whether the population mean is equal to some target value. So for this scenario, we will apply one sample mean test. And then we have two tests for one sample mean test, Z test and T test. So when to apply z-test? When the population standard deviation is known, then we will apply z-test. Majority of the circumstances, you will not be aware of the population metric. You will be aware of only the sample metric. So majority of the circumstances, you will be aware of only the sample standard deviation. So that being the case, you will end up applying t-test for solving these exercises, right? So you'll be applying one sample t-test for solving these exercises. So population standard deviation is given, then we will apply z-test. But sample standard deviation alone is known and it is given in the case scenario. we will apply t-test. So that is the logic. That is the criteria. And if the sample size is going to be in excess of 30, we can apply either z-test or t-test. It will not make any difference. So the sample size is greater than 30. We can apply either z-test or t-test. We will not see any difference, right? So this is the criteria that we need to apply for deploying z-test and t-test, right? So this is as far as one sample mean test is concerned. And the second hypothesis test under mean is two sample mean test. Again, two samples Z or T test. So the criteria as to whether we need to apply Z test or T test is the same as we saw for one sample mean test. But then in two sample mean test, as the name itself suggests, the samples will be drawn from two different population categories. And we would be comparing the population means of these two categories. Say, for example, there is mean weight of production, right, reported by multiple production centers, say production center A and production center B. So if you want to compare the population mean weight of production pertaining to these two production centers, production center A and production center B, then we need to perform two sample mean test, right? So we can find out whether the population mean weight of production pertaining to production center A is greater than production center B or less than production center B or not equal to production center B. So whatever it is, so we can test it out and then find out, right? So if you want to compare the population means of two different population categories, then we will perform this two sample mean test. Again, whether to apply Z test or T test, the criteria is pretty much similar. So the population standard deviation is known, Z test. Sample standard deviation alone has been provided for you. Then we need to apply T test, right? And then we have what is called pair T test. So it might actually sound similar to two sample mean test. So pair also we will be, comparing two population means, right? So what is the difference between this two sample mean test and the pair T test? So two sample mean test, as we just now saw, can be applied when we want to compare the population means of two different population categories like production center A and production center B, right? But then the PAT-T test will be performed if you want to compare the population means of two different scenarios in a process, right? Say you've done some automation in your process and you want to validate whether the automation is successful or not. So what you will do? You will consider some metric and then try to compare the metric performance in the pre-automation scenario versus the post-automation scenario. Suppose you want to compare processing time as a metric, then what we will do, we will have the mean processing time pertaining to the pre-automation scenario, and we will have the mean processing time pertaining to the post-automation scenario, and we will compare these two. So if the automation is successful, ideally the mean processing time in the post-automation scenario should have got significantly reduced compared to the pre-automation scenario, right? So then only we can say that the automation is successful. So here in PAT T-test, as we can see, we are comparing the population means of two different scenarios existing in a process. So in case of two sample mean test, we would be comparing the population means of two different population categories. It could be two different processes or two different production centers. But then PAT test, we are comparing the population means pertaining to two different or two different scenarios existing within a process, right? Like pre-automation scenario versus post-automation scenario, right? Understood the difference between two sample mean test and the PAT-T test. So there is small line separating these two, but then we need to be careful, right? When we decide whether we need to apply two sample mean test or PAT-T test for a given scenario where it involves two population categories, right? So if it is different population categories, then two sample mean test, but then it's two different scenarios existing within a process, then we will use PAT-T test. And then finally, we have ANOVA, analysis of variance. So analysis of variance will be applied if you want to compare the population means of more than two population categories. So if you have only two different population categories to be compared, then we will use this two sample mean test, two sample Z test or two sample T test. But then if you have more than two population category means to be compared, then we cannot, perform multiple two sample t tests. It will be highly challenging. So we have a single test called ANOVA. Say, for example, you want to compare the population mean mileage of 6 brands of motorcycles, right? So with one test, we will be able to do this comparison, and that test is ANOVA. So moment we find more than two population category means to be compared, then we need to think of applying this hypothesis test called ANOVA. And as I told you, even though it is titled as analysis of variance, it is actually a mean test. So we'll find out how it is a mean test when we solve an exercise under ANOVA on the 11th day of this training session. So these are the 4 tests that we have for mean, and this is the maximum. So for all the other matrices, we will not have so many tests. Only for mean, we will have these 4 tests which can be applied for different scenarios, right? And then moving on to the next metric, which is median. So as I told you, median is the statistical metric that we would apply when the data distribution is non-normal and non-random, or if you find any outlier value present in the data set. So these median tests are also called as non-parametric tests, right? So if there is a question wherein you are asked to identify a non-parametric test from the given list, so you need to pick the median test from that list, right? So all the other tests will be called as parametric tests, but median tests alone will be referred as non-parametric tests. And last Friday itself we saw, right? So the sample mean is denoted by this notation. So we put small x and we put a curve at the top. So if you put a bar at the top, it will become sample mean. But then if you put a curve at the top, it will become sample median. But then there is no notation for population median. That is why we didn't include median as a statistical metric in that table, right? So what are the various tests that we have for median? The first one is one sample signed rank test. And this one sample signed rank test is the equivalent median test for one sample mean test, wherein we would validate whether the population median is equal to some target value. So in the same bike example, so if the data was non-normal, if the mileage data was non-normal, then we would need to validate whether the population median mileage of the new brand of motorcycle is exceeding 50 kilometers per liter, right? So if the data is non-normal, then obviously we would need to use median. But then we are dealing with the continuous data, right? So we need to remember that. So we are not going to use any other data here. We are using the continuous data. Only thing is when the data distribution is non-normal or non-random, then we would be applying median. But the scenario will be pretty much similar to what we saw for mean, right? So only difference is here we would be validating whether the population median of a certain metric is equal to some target value, right? And then we have what is called Mann-Whitney test, and this is the equivalent median test for two sample mean test. So if you want to uh, compare the population medians of two population categories, then we will use this Mann-Whitney test. And then we have Kruskal-Wallis test and Moore's median test. So Kruskal-Wallis test and Moore's median test are the equivalent median test for ANOVA, right? Wherein we would want to compare the population medians of more than two population categories. So if you want to compare the median processing time pertaining to 3 different shifts, in a process, then we will use this Kruskal-Wallis test or Moore's median test. But then when to apply Kruskal-Wallis, when to apply Moore's median, we will find out when we work out that exercise under ANOVA on the 11th day. But for now, understand that Kruskal-Wallis test and Moore's median test are the median tests for ANOVA, right? Wherein we would be comparing the population medians of more than two population categories, right? So these are the median tests that we have. And the third metric that we are going to see is variance. So variance, standard deviation, we all know are pretty much similar matrices. So whether it is variance or standard deviation, we will use the same test that we are seeing here, right? So variance and standard deviation again needs to be applied only if the data distribution is normal. So if the data distribution is non-normal, and if you are going to calculate variance or standard deviation, so it will be a huge value, right? So it will not be a clear-cut representation of that variation in the data set. So variance and standard deviation, the conventional formula can be applied only if the data distribution is normal. So variance test, we have one sample variance test, which is also called as chi-square test. So this one sample variance test, as the name itself suggests, the samples will be drawn from a single population category, and we would want to validate whether the population variance of that category is equal to some target value. Say, for example, as part of your Six Sigma project, you have reduced the variance or standard deviation significantly, and you would want to validate whether the variance, the population variance, is below some value. Say population variance is less than 5 minutes. So if you want to validate this claim, then we will be using one sample variance test for that scenario. And this one sample variance test is also known as chi-square test. And then we have two sample variance test, which is also called as F test. So when you will use this two sample variance test or F test, when we want to compare the population variances of two population categories. So here the samples obviously will be drawn from two population categories, and we would want to compare the population variances of these two population categories. Then we will use this two sample variance test, which is also called as F test, right? So F test, the test statistic or the F test calculated value will provide the ratio of variances drawn from a normal population. So there can be a question on this. So that is why I've included this one-liner. So which test statistic would provide the ratio of variances drawn from a normal population will be the question. So we need to pick the option F test, right? So that is the correct option. So here we would be comparing the variances, the population variances of two population categories, right? So you want to compare whether the variance in the processing time pertaining to shift 1 is less than the variance in the processing time pertaining to shift 2, then we can perform this two sample variance test, which is also referred as F test. And then finally, we have Bartlett's test under variance. So this Bartlett's test is similar to ANOVA and Kruskal-Wallis test, wherein we would compare the population variances of more than two population categories. So if we had only two population categories given in the case scenario, and if we want to compare the population variances of these two population categories, then we would perform this two sample variance test. But then if you want to compare the population variances of more than two population categories, then we need to use Bartlett's test. Say, for example, there is a, average processing time data given for some three production centers, and you want to compare the variance in the processing time. And we will use the Bartlett's test because we have three population categories to be compared, right? And then moving on to the discrete data. So first we are going to look at the binary discrete data or the defectives type of data. So we have this metric called proportion. So proportion is the primary metric for representing binary discrete data. We all know that, right? So under proportion, we have one proportion test and two proportion test. So when to apply one proportion test? So one proportion test, as we can see, the samples will be drawn from a single population category, and we would want to validate whether the population proportion of that category is equal to some target value. Say, for example, you have improved the accuracy percentage for your process, right? And you would want to validate whether the accuracy percentage is greater than 95%. So accuracy percentage, we all know, is a binary discrete metric. We already seen, right, when we discussed about the binary discrete data and the data types, right? So accuracy percentage is a binary discrete metric. And if you would want to validate whether the population accuracy percentage for a given process is greater than 95% or whatever value, then we need to perform this one proportion test. And then we have two proportion test. So two proportion test, as the name itself suggests, the samples will be drawn from two population categories, and we will be comparing the population proportions of these two categories. Say, for example, you want to compare the defective proportion of shift 1 and shift 2. You would need to perform this two proportion test, because defective proportion, as we all know, is again a binary discrete metric. Because when we inspect a sample unit, the sample unit can either be defective or accurate. So defective proportion is exactly opposite to the accuracy percentage or the accuracy proportion. So defective proportion will also be considered as binary discrete metric. So here we are comparing the proportion of a binary discrete event pertaining to two population categories, that is shift 1 and shift 2. So if you want to validate whether the defective proportion of shift 1 is less than that of shift 2, then we need to ideally perform this two proportion test, right? And then moving on to average, which is the metric for representing the count discrete data. So average, we have couple of tests under that. So we have one sample Poisson rate test and then two sample Poisson rate test. So one sample Poisson rate test, obviously the samples will be drawn from a single population category, and we would want to validate whether the population average of a count discrete event is equal to some target value. Say, for example, you have reduced the average number of defects below a certain value, right? And you want to validate whether the population defect rate is below that value or not, then we need to perform this one sample Poisson rate test. Suppose you want to validate whether the population defect rate is less than 5 per day or less than 2 per day, then we would perform this one sample Poisson rate test. Because when we talk about count discrete data, it is defects type of data. So the binary discrete data, it will be defectives type of data, right? We need to be very clear with regard to the difference between defect and defective. And that is what we saw when we discussed about the process capability analysis for discrete data, right? And then we have two sample Poisson rate test. So as the name itself suggests, the samples will be drawn from two population categories, and we would be comparing the average of the count discrete event pertaining to these two categories, right? Say, for example, you want to compare the average number of units produced, right? The average number of units produced per hour pertaining to process A and process B. So average number of units produced per hour is nothing but the productivity, right? So this is the formula for productivity. So average number of units produced per hour. So if you want to compare this metric for couple of processes like process A versus process B, then we need to perform two sample Poisson rate test, right? So one sample Poisson rate test and two sample Poisson rate test for average, which is the primary metric for representing a count discrete data. And the final hypothesis test that we are going to look at is chi-square contingency table. And this chi-square contingency table is also referred as test for dependency. So what do you mean by test for dependency? So out of the two variables, y variable and x variable. So y variable would denote the effect variable. X variable would denote the cost variable. So out of these two effect and cost variables, which one will be referred as the dependent variable? Which one will be referred as the independent variable? So we all know that effect cannot happen on its own. So the effect will always be driven by a single cause or multiple causes, right? So there is a dependency for effect on the cause. Otherwise, effect cannot take place at all unless and until a single cause or multiple causes, drive that effect. Effect cannot take place at all, right? So effect will be called as a dependent variable and cause will be referred as the independent variable. So as part of this chi-square contingency table exercise, we would be validating whether the y variable given in the case scenario is dependent on the x variable or not, right? So we would be validating whether the y variable is dependent on the x variable or not in this chi-square contingency table exercise. So a chi-square contingency table, the input values will be given in a table format. The input values will be given in a table format. And if you say table, obviously we need to understand there will be minimum of two rows and two columns. Then only we can call that as a table. So there will be minimum of two rows and two columns. And the input values will be discrete values. So we will not have the continuous data as input values. The input values out and out will be discrete values in this chi-square contingency table. Clear? Say for example, say you want to validate whether the sale of mobile brands is dependent on the income levels of the people living in a society. So you have varied income levels and we have varied mobile brands. So you want to find out or validate whether the sale of mobile brands is dependent on the income levels of the people, whether people belonging to a particular income level is preferring a particular mobile brand or not is what we will try to validate through this chi-square contingency table exercise, right? So if you find that a specific group of people, right, belonging to a income level category, they are preferring a particular brand of mobile phone much more than the other ones, then what the mobile manufacturer will have to do? So he has to ensure that he keeps enough stock of that mobile phone meant for that particular income level category people, right? So this is the kind of business decisions that one can take by performing this chi-square contingency table exercise, which is also called as test for dependency. So all the other hypothesis tests, if you see, we will have the population notation incorporated in the hypothesis statement. But that is why we also learned about the population notations for all these statistical matrices, right? Last Friday. So what did I say? What did I tell at that time? I said very clearly that when we frame the hypothesis statements, we need to ensure that the population notation of that statistical metric is incorporated. So we should not have the sample notation of the population or sample notation of that statistical metric written as part of the hypothesis statements. If you are writing the sample notation for a statistical metric, that means you have not understood the concept of testing of hypothesis. Because as I told you, testing of hypothesis, the assumption is made about a population metric, right? And we are validating whether our assumption is valid or not. So we are validating whether our assumption is correct or not with regard to that population metric. right? So that being the case, so in the hypothesis statements, we should be incorporating only the population notation for a given statistical metric. So all the other hypothesis tests, if you see, we would have actually come up with the population notation for that specific statistical metric as part of the hypothesis statements. But for chi-square contingency table, the hypothesis statement will be in a text format. The null hypothesis will be the y variable is independent of the x variable. So in the chi-square contingency table exercise, we need to identify which one is the y variable, which one is the x variable. So there will be two variables given. So we need to first and foremost identify which one is the y variable and which one is the x variable. So y is the effect variable, x is the cost variable. So once we do that, right, so we would be framing the hypothesis statements as null hypothesis will be the y variable is independent of the x variable because the dependency is something that we need to prove through this chi-square contingency table exercise. So that will be my alternate hypothesis. So the alternate hypothesis here will be the y variable is dependent on the x variable, right? So here in case of sale of mobile brands and income levels of the people, which one will be Y, which one will be X? So sale of mobile brands is the ultimate impact that one can experience. So that will be the effect variable, right? So that will be my Y variable. And the income levels of the people is going to drive the sale of mobile brands. So the income levels of the people is going to be my X variable. Clear? Now, these are the various hypothesis tests that we have for all these statistical matrices. So on the 11th day, when we are going to solve the exercises under hypothesis testing, so we will look at the exercises under one sample t-test, two sample t-test, pair t-test, and also ANOVA. So we will cover all the four hypothesis tests under mean. And then variance, we will perform an exercise for two sample variance test and also Bartlett's test. Proportion, we will do an exercise for one proportion test and two proportion test. And finally, we will also look at an exercise under chi-square contingency table. So these are the various exercises that we are going to solve on the 11th day of this training program because the exercises under testing of hypothesis will be a black belt specific curriculum. But then we are not going to get any of these exercises as questions in the black belt final assessment. So as I told you, we will be given only the scenarios and you'll be asked to validate or we'll be asked to identify which hypothesis test logic we need to apply for that case scenario. That's it, right? So that being the case, you will not be asked any questions pertaining to the exercises under hypothesis testing, right? You'll not be asked any question pertaining to the exercises under hypothesis testing. So all those exercises that we are going to solve on the 11th day, it's done more from a black belt point of view. As a black belt, you need to know how to deal with those case scenarios, right? So just for gaining knowledge as a black belt, not from an assessment point of view. Fine. So let us move on to the next section wherein we are going to look at this important metric called p-value. So we have actually referred to this p-value multiple number of times, right? So previously we have looked at this metric called p-value multiple number of times. So if you would remember for the run chart exercise, I had mentioned that we need to look at this metric called p-value if you are creating the run chart using Minitab. Similarly, when we perform the normality test in Minitab, we again looked at this metric called p-value. So p-value is going to be a very, very important metric, right, provided by Minitab. So whenever we deal with sample data and make an inference about the population, as I told you, the testing of hypothesis as a concept would be very much relevant for that scenario. So whenever we perform testing of hypothesis, we will be looking at this p-value and then we'll be taking a call as to whether we are supposed to accept the null hypothesis or reject the null hypothesis, right? So p-value, the full form is probability value. And what is this? This is the probability of accepting the null hypothesis. Because I told you that all the decisions in hypothesis testing will be taken from the null hypothesis perspective. So we will either accept the null hypothesis or reject the null hypothesis. So if you happen to reject the null hypothesis, then there is no other option but to accept the alternate hypothesis. So p-value is actually the probability of accepting the null hypothesis. So the p-value is going to be very high, then the probability of accepting the null hypothesis will be bright. But then the p-value is very low, then the probability of accepting the null hypothesis will also diminish, will also become less, right? And in that case, we'll end up accepting the alternate hypothesis. But then what is the criteria that we are supposed to apply for p-value? So p-value greater than 0.05 for 95% confidence level, we will accept the null hypothesis. Now, this 0.05 has some relevance. In fact, one of the participants asked me this question, why we need to apply 0.05 as the criteria for p-value. So I told her that please wait till we discuss about this as part of the analyze phase. Right now, it's the time for us to discuss about this 0.05 as the criteria value for p-value because we have learned about the confidence level. Right? So now we will be able to clearly understand. Now, 0.05 as the criteria for p-value can be applied only if the confidence level is 95%. If the confidence level is 90%, then the criteria for p-value would change to zero point 0.1 or 10%, right? 0.05 is 5%, correct? So 0.05 as a criteria for p-value will hold good only when we have the confidence level as 95%. But since I had mentioned that the default confidence level that would be considered in a hypothesis testing scenario will be 95%, for majority of the case scenarios, we will apply the criteria for p-value as 0.05. Clear? But we should not take it as a blanket criteria for p-value. So it all depends on the confidence level which you are assigning for a particular case scenario. Nothing specific is mentioned about the confidence level. 95% will be considered as the confidence level. In that case, 0.05 can be safely considered as the criteria for p-value. Right? But then as a black belt, you need to know that this 0.05 is not a blanket criteria. And this is how majority of the people are thinking, right? So they think that 0.05 is a blanket criteria, which is not the case. So that is why I'm clearly mentioning the confidence level as well. The earlier problems, I did not mention the confidence level because you were not aware of it. Now that you are all aware of this confidence level, so I can safely mention the confidence level as part of my inference, right? So p-value greater than 0.05 for 95% confidence level, we will accept the null hypothesis, right? So if it is 90% confidence level, as I told you, the criteria would change to 0.1 or 10%. If it is 99% confidence level, the criteria would change to 0.01 or 1%. So 0.05 as criteria for p-value would be applicable only if the confidence level is 95%, but then 95% is the default confidence level, right? So p-value greater than 0.05 for 95% confidence level, we will accept the null hypothesis. On the other hand, p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis. So the p-value is going to be less than 0.05, then the probability of accepting the null hypothesis will become very less. And in that case, you will end up rejecting the null hypothesis and accepting the alternate hypothesis. So this will be the criteria, right, that we will apply by looking at the p-value and take a final call as to whether we are supposed to accept or reject the null hypothesis. So I told you, whenever we deal with sample data, the testing of hypothesis will be very much relevant for that particular scenario. So let us also look at the normality test, right, and see how to frame the hypothesis statements. So here again, in the normality test, we would be dealing with the sample data and then performing this normality test, the result of which will be applied to the entire population, right? So that is the beauty of all these statistical tools. So normality test also we would be dealing or we would be validating the sample data, and then we would try to find out whether the inference that we make is applicable to the entire population, right? So here again, when we deal with sample data, as I told you, testing of hypothesis as a concept would be very much relevant. So obviously we need to frame the hypothesis statements even for this normality test scenario, right? So what will be the hypothesis statements for the normality test scenario, right? What will be the null hypothesis here? H naught. So I told you that null hypothesis should reflect the status quo or the ideal scenario. So when you see a group of people, what would be your thought process about them? So you'll always think that the group of people are quite normal, right? So the abnormality is an exception. So one or two people in that group could be abnormal. But then unless and until that abnormality is proved, we will continue to consider that the people are normal. Similarly, when it comes to a data distribution, you'll always think that the data distribution is normal unless and until it is proved that the data distribution is non-normal. Clear? So what would be the null hypothesis for normality test? Anyone? Data distribution is yes, please. Just make an attempt. So what will be the null hypothesis for normality test?
The data
The data
distribution
distribution
is
is
normal,
data distribution is
normal or continuous.
normal. Exactly. The data distribution is normal. Because this is my status quo scenario. Just like how I see a group of people and think that they're all normal people, because abnormality could be an exception, right? It's not like, all the people would be abnormal, correct? So in a group, couple of people could be abnormal. But then when you look at the group, you'll always think that the entire group consists of normal people. Similarly, when it comes to a data distribution, we'll always think that each and every data distribution is normal. So the abnormality would be an exception which we need to prove, and that will be part of my alternate hypothesis. So the alternate hypothesis for this normality test will be the data distribution is non-normal, right? So that is why I told you that if the p-value is greater than 0.05, then we need to accept that the data distribution is normal. On the other hand, if p-value is less than 0.05, the data distribution will be considered as non-normal. And this is how it is, right? Because the null hypothesis for a normality test will always be the data distribution is normal, right? And the alternate hypothesis will always be the data distribution is non-normal. So p-value greater than 0.05 for 95% confidence level, we will be accepting the null hypothesis. So what is the null hypothesis? Data distribution is normal. So that's why I told you p-value greater than 0.05, we will infer that the data distribution is normal. So p-value less than 0.05, we will be inferring that the data distribution is non-normal. Similarly, for this run chart scenario, so what will be the null and alternate hypothesis statements? So now that we have learned about the concept of hypothesis testing and also understood how to frame the hypothesis statements, so it should not be a challenging one for you. So what will be the null and alternate hypothesis for this run chart scenario? So what is that we are trying to do in a run chart scenario? We are trying to validate whether the data distribution is random or non-random, right? So what will be the null hypothesis? So the status quo scenario or the ideal scenario will be the data distribution is random, right? So the ideal scenario will always be the data distribution is random, because when it comes to the types of variation, the ideal scenario would be that the process will always be influenced by common cause variation, right? So the process being influenced by assignable or special cause variation will be an exceptional scenario. So that being the case, the common cause variation would indicate that the data distribution is random, whereas the influence of assignable cause variation would indicate that the data distribution is non-random due to any of the four non-random characteristics, right? So for null hypothesis, in this run chart scenario will always be the data distribution is random, right? So that's why I would have told you, if p-value is greater than 0.05 for all the four non-random characteristics, then we need to infer that the data distribution is random. And the alternate hypothesis will be the data distribution is non-random due to any of the four non-random characteristics, right? So that's why p-value less than 0.05 for any of the four non-random characteristics, we would infer that the data distribution is non-random due to that specific non-random characteristic. Fine. So now you can always, correlate all these hypothesis statements with whatever, exercises that we solved earlier.
Sridhar, quick
Yeah.
question on the last, this slide and the next one. Here we are looking at the HO and HA, and we are
Mm,
finding out the p-value.
mm.
Where do we see the confidence level in this particular exercise?
No. That is something that you need to assign.
Okay.
Confidence level will
Mhm,
not be calculated as such. We need to assign the confidence level. Suppose you want to be more confident about the population result, then
mhm,
we will assign a higher level, say 99%. But then we need to understand that the confidence interval also will be very, very wide. Correct?
mhm,
So that is what we saw. So you are, allowing more allowance for the confidence interval. So you do not want to come up with a precise result about the population, and you are okay with having a wider confidence interval, then we can assign a higher confidence level for that scenario. But nothing specific is mentioned about the confidence level. 95% is what we need to consider as a confidence level. So only if it is
okay.
95%, this 0.05 as a criteria for p-value will be applicable.
Yeah. I was just trying to correlate,
Yeah.
like how did we reach 0.05 on this scenario?
No. This is nothing. This confidence level is not mentioned here, right?
Yeah.
So
Right,
the
right.
default confidence level will be considered as 95%.
Oh, okay.
Okay. That is what majority of the scenarios will actually consider, right? So the default, because nothing specific will be mentioned,
Hmm.
except when you are performing some clinical trials, right? Some medical clinical trials and all those stuff, where you would want a higher confidence level to be assigned for the results. Then in that case, we will work at 99% confidence levels. In which
Hmm.
case, the width of the confidence interval will also be much wider, right? But otherwise, for majority of the scenarios, we will be having 95% as a confidence level. In fact, the example that we saw last week, right, when we discussed about the confidence interval, the margin of error. So I had given the exit poll results as an example, right?
Right.
So nothing specific would have been mentioned about the confidence level whenever they publish the exit poll results. So they would come up with a confidence interval. That is, they will give an interval estimate with regard to the number of seats that are
Hmm.
likely to be won by a particular political party. But they wouldn't have mentioned anything about the confidence level. So if you notice, right? So we need to understand. So if once we learn all these things, right, we can easily understand that they have actually estimated this, confidence interval at 95% confidence.
Okay.
Fine. So this is about the p-value. So if you want to remember this in the form of a slogan, right, we can do so. So P low, null go. So P is less than the criteria value. So P low, null go. Right? Null hypothesis will get rejected. P high, null fly. So P is greater than that criteria value, null will fly. That is, null will be accepted. So these kind of catchy slogans, we can easily remember, right? So it will be uh, absolutely simple for us to kind of come up with an inference by looking at the p-value. But then, let me tell you, if you're using my template, even the final decision will be provided to you, right, based on the p-value. So you don't have to really remember all these criteria. So automatically it will apply. Depending on the confidence level, it would actually automatically apply the relevant criteria for p-value and will provide the final decision. So if you see the template, right, for the hypothesis testing exercises, which we are going to see on the 11th day of this training session. So if you look at the one sample t-test exercise, so this is the template I've given for the one sample t-test. So if you see here, we have the p-value and we also have the final inference based on this p-value. Of course, this accept H naught is a default inference. So we should not consider this unless and until we provide all the input values in this input section, right? Only then we need to look at the inference. So the inference will change according to the p-value, right? So in Minitab, they will stop with providing the p-value. Then we need to come up with the final inference, right? So based on the criteria that we discussed just now, right? But then in this template, if you see, we'll not only have the p-value, but we'll also have the final inference. So you don't have to really remember the criteria logic that you need to apply for taking a decision, right? So it will automatically change. And one beautiful thing here is it will change according to the confidence level. So some of the exercises at 95% confidence level, you might end up accepting the null hypothesis, but at 99% confidence level, so the decision could be something else, right? Or 99% confidence level, you would be accepting the null hypothesis. At 95% confidence level, you'll be rejecting the null hypothesis, right? So that being the case, it will automatically change based on the confidence level that you would provide in this input section. So when you use this template, you don't even need to remember the criteria logic that we are supposed to apply for this p-value and then take the final decision. Fine. So let us move on to the next section in the analyze phase. So once we have validated the significance of each and every vital cause with respect to the business problem, we now need to establish the relationship between the cause and the effect. So pictorially, we would be able to establish the relationship between any two variables using the scatter plot. And then if you want to objectively measure the strength of the relationship, then we need to perform correlation analysis, right? So when we actually plot a scatter plot, so we can get three types of graphs, right? So let us look at three different scenarios that we can get when we plot the data in a scatter plot. So the graphs can actually look like this. So the first scenario, when we plot the data for the x and y variables, and if you get an upward slope like formation of data points like this, right? So when we plot the data points for x and y variables, and if you observe an upward slope like formation of data points like this, then we can infer that the two variables are positively correlated. So X and Y are positively correlated. So what do you mean by positive correlation? An increase in the X variable would result in increase in the Y variable as well, right? So increase in the X variable would result in increase in the Y variable as well. So that is when we would say that the two variables are positively correlated, right? Or a decrease in the X variable would result in decrease in the Y variable. So what are the examples that we can give for positive correlation? Say experience levels of the associates and the quality levels or the accuracy levels. So it's a known fact, right? It's a common logic that if an employee gains more experience working in a process, the employee would obviously gain more expertise working in that process and will commit lesser number of errors, right? So his quality level or the accuracy level is bound to improve as he gains more experience working the process. So experience levels go up, we will see an increase in the quality or the accuracy levels. So these two variables will be positively correlated. And similarly, demand and price. As the demand for a product goes up, what will happen to the price? The price will also go up. So demand and price will be positively correlated. So like this, you can think of various examples wherein the two variables will have positive correlation. That is, both the variables will be moving in the same direction, right? So the X variable, the cost variable is the one which will trigger the effect variable. So the cost variable is going to move in a particular direction. The effect variable also will move in the same direction. Then we will say that the two variables are positively correlated. And if you are going to plot the data points pertaining to the X and Y variables, we will get a upward slope like formation of data points in a scatter plot. And the second formation could be something like this. Again, when we plot the data points for X and Y variables, you find a downward slope like formation of data points. So what can we infer from this? We can say that X and Y are negatively correlated, right? Exactly opposite to the first scenario. So when we observe a downward slope like formation of data points in a scatter plot, we can say that X and Y are negatively correlated. So what do you mean by negative correlation? X increases, Y will decrease, or X decreases, Y will increase. So both these variables will move in the opposite direction, right? So X is moving in a particular direction, the Y will move in the opposite direction, right? Then in that case, we will say that both these variables are negatively correlated. So what are the examples we can give for negative correlation? Again, experience levels of the associates and the average processing time, right? So as I told you, employee gains more expertise working in a process. The employee will be able to handle that process within a shorter time frame. So more experience means the employee will be able to complete execution of the process within a shorter time frame. So the average processing time is bound to reduce when we have the employee experience levels going up. So both these two variables are negatively correlated, right? And then we can say supply and demand, right? When supply increases, the demand for that product will definitely reduce. So there is abundance of supply in the market, right? With regard to that product, obviously the demand for that product is likely to reduce. The same way, supply decreases, the demand will increase. So supply for that product decreases, then the demand for that product is likely to increase. So supply versus demand would be negatively correlated. So like this, as I told you, you can think through many examples pertaining to negative correlation. And then the third scenario, when we plot the data points pertaining to the X and Y variables, and if you observe random plotting of data points without any slope right here and there, then we will say that X and Y are not correlated. That means there is no relationship between these two variables. So X and Y are not correlated. So these are the three scenarios that we would be able to observe when we plot the data points pertaining to the X and Y variables in a scatter plot, right? So what we are going to do, we are going to look at an exercise under correlation and regression analysis. Anyway, this exercise we are going to solve on the 11th day of this training program. But for now, let us try to create the scatter plot and then find out whether there is a positive correlation existing between the two variables or a negative correlation existing between the two variables, or there is no relationship at all, right? So the two variables that are provided here are experience levels of the associates in months and the average processing time in minutes. So just now we saw that logically speaking, these two variables will have negative correlation. So as the experience levels of the associates increases, the associates will be able to execute the process within a shorter time frame. So experience levels and the average processing time, logically speaking, would be negatively correlated. But then let us, construct the scatter plot for this practical data that we have and see whether they are negatively correlated or not. So let me use Minitab first and then create the scatter plot. And then I will show you how to create the scatter plot using Excel. So let me just copy paste the data points pertaining to the X and Y variables. And for creating scatter plot in Excel in Minitab, so we need to go to graph. The first graph itself is scatter plot. Just click on that. So we will have the scatter plot with the regression slope. So you'll understand the importance of the regression slope when we solve that problem under correlation and regression analysis. And we click OK. So what is the Y variable here? Average processing time is the Y variable. So out of these two variables, experience level and the average processing time. So experience level, we all know, would actually trigger this average processing time. So average processing time would be the ultimate impact. So whichever is the ultimate impact that one would experience, that variable needs to be considered as the effect variable. And the one that is driving this effect variable will be considered as the cost variable. So here the experience levels will be driving the average processing time. So average processing time will be your Y variable and the experience levels will be your X variable. And then let me construct the scatter plot for this. So as we expected, we see a downward slope like formation of data points, which would clearly indicate that the experience levels of the associates and the average processing time are negatively correlated, which means an increase in the experience levels of the associates would result in decrease in the average processing time and vice versa. Vice versa means the opposite side also will hold good. What is the opposite side? That is a decrease in the experience levels of the associates would result in increase in the average processing time, right? So they are negatively correlated. But then we do not know what is the strength of this negative correlation. So that we can ascertain when we perform this correlation analysis, right? So we know that these two variables are negatively correlated by looking at the scatter plot. But we will not be able to tell about the strength of this negative relationship. So that can be ascertained when we perform the correlation analysis. But then if you are going to construct the scatter plot using Excel, so we can do so, just highlight the two columns containing the data points for the X and Y variables and then go to insert. Under recommended charts, you see the one with all these dots. Just click on that. The first one itself is scatter plot. So as I told you, the Minitab output will be much better than the Excel output. But then when we construct all these graphs using Excel, we will at least have some kind of a information, right, which we can derive by looking at this graph. Otherwise, if you want a better output, obviously we need to use Minitab and then obtain the same, right? So Minitab will have all these, legends, everything. It looks, even presentation-wise, this is a very old version of Minitab, right? Whatever I'm using, very old version of Minitab, the latest versions will have much better aesthetics as far as graphs are concerned. Fine. So this is about the scatter plot. So we can only, infer that there is a negative relationship between these two variables. But then what is the strength of this negative relationship is something we can ascertain when we perform the correlation analysis. So we will come back to this on the 11th day of this training session. When we work on this exercise, we'll also look at this scatter plot, right? Fine. So let me go back to the notes file. So let us revise this once again quickly. So scatter plot, as I told you, is a graphical format for establishing the relationship between any two variables. Here we are talking about cause and effect. So what are the three scenarios that we can get in a scatter plot? So when we plot the data points for the x and y variables in a scatter plot, and if you observe an upward slope-like formation of data points, we can infer that x and y variables are positively correlated. What is positive correlation? If there is an increase in the x variable, there will be an increase in the y variable as well, and vice versa. So experience levels of associates with versus the quality score or demand versus price, etc. Then when we plot the data points for the x and y variables in a scatter plot, and if you observe a downward slope like formation of data points, we can infer that x and y variables are negatively correlated. Meaning, if there is an increase in the x variable, there will be a decrease in the y variable and vice versa. So, for example, experience levels of the employees versus average processing time, supply versus demand, etc. The third scenario, when we plot the data points for the x and y variables in a scatter plot, and if you observe random plotting of data points, we can infer that there is no relationship existing between the two variables, right? That's the third scenario. Now, as I told you, if you want to ascertain the strength of this relationship, then we need to perform correlation analysis, right? So correlation analysis will help us to ascertain the strength of the linear relationship between any two variables. So what would you call as linear relationship? Suppose in a scatter plot, you have the slope-like formation of the data points, then the relationship will be considered as linear, right? So you can get different shapes and different formats of the plotting of data points. But if you get a slope-like formation of data points, we can say that the relationship between the two variables is linear. And when we perform the correlation analysis, we will not be able to ascertain the strength of the relationship between the variables pertaining to any kind of formation of data points in a scatter plot. So we will be able to ascertain the relationship only for the linear relationship, right? So it should have a slope-like formation of data points when we plot the scatter plot. For those kind of scenarios alone, we will be able to ascertain the strength of that relationship through correlation analysis, right? So here, in case of correlation analysis, we'll be using a metric called correlation coefficient, which is denoted by small r. So small r would stand for correlation coefficient. And this small r can take any value between -1 and +1. So there is a formula for calculating the small r. So there is a manual formula, there is an Excel formula. So we will be looking at the Excel formula on the 11th day of this training session. So when we apply a formula to calculate this r value, so this r value will always be between -1 and +1. So it will not exceed beyond these limits, or it will not be less than -1, right? So it will be between -1 and +1, right? So that being the case, right? So when the R value is closer to +1, we can say that the two variables are positively correlated, right? So when the R value is closer to +1, we can say that the two variables are positively correlated. On the other hand, if the R value is closer to -1, then we can say that the two variables are negatively correlated. But then the R value is closer to 0, then we will say that there is no correlation existing between the two variables. So this is how we would infer by looking at the R value or the correlation coefficient value. But then if you want to come up with a perfect inference, right? Or you want to come up with a correct inference by looking at the R value. So you can always refer to this particular table, right? So you can always refer to this particular table because the final assessment, you will not be asked to calculate the correlation coefficient value. You will be given the correlation coefficient value in the question and you'll be asked to infer, right? So you'll not be asked to perform any exercise pertaining to correlation analysis, but then you'll be provided with the correlation coefficient value and you'll be asked to infer. So you can always refer to this table. So the correlation coefficient value is going to be greater than plus 0.85. So what is the inference we can come up with? We can say that there is a strong positive correlation existing between the two variables. So when it is greater than plus 0.85, that means it will be closer to +1. So in that case, we will say that there is a strong positive correlation existing between the two variables. On the other hand, if the correlation coefficient value is going to be between 0.85 plus 0.85 and plus 0.5, then we will say that there is a weak positive correlation existing between the two variables. But then if the correlation coefficient value is going to fall anywhere between plus 0.5 and minus 0.5, that means it will be closer to 0. Then we will say that there is no correlation existing between the two variables. On the other side, if the correlation coefficient value is going to be between minus 0.5 and minus 0.85, then we will say that there is a weak negative correlation existing between the two variables. Finally, if the correlation coefficient value is going to be less than minus 0.85, which means it is closer to -1, then we will say that there is a strong negative correlation existing between the two variables. So between minus zero point 0.5 and between minus zero point 0.5 and minus 0.85, we will say that there is a weak negative correlation. But less than minus 0.85, that means it is closer to -1, we will say that there is a strong negative correlation. So you can always refer to this table and then provide the appropriate inference, right, for a given correlation coefficient value. So the final section in the analyze phase is going to be regression analysis. So again, I repeat, the exercises under testing of hypothesis as well as the correlation and regression analysis will be solved on the 11th day of this training session. So as part of the common curriculum, we'll be looking at only the concept of correlation analysis and regression analysis, right? So the exercise will be solved on the 11th day, which will be under the black belt specific curriculum, right? So if you are asked to identify a tool which would help us to establish relationship between any two variables, then we need to pick the option either scatter plot or correlation analysis or regression analysis. So all these three tools that we have seen that we are looking at right currently. So all these three are relationship establishing tools, right? So moment you find relationship as part of the question and you are asked to identify the tool, then we need to pick either scatter plot or correlation or regression from the multiple choice. Clear? So all these three are relationship establishing tools. So the final thing that we are going to look at is regression analysis. So regression, both correlation and regression, as we can see, would help us to estimate the relationship between the cause and effect. So even when we perform the regression analysis, we would be able to estimate the quantum of the relationship between the cause and effect. So in the regression analysis, as we all know, so we will try to build a regression model, right? We will try to establish the relationship in the form of a regression model. So which will be in the format y is equal to f of x plus epsilon. So this is something that we have already seen as part of the introduction phase when we wanted to demonstrate that common cause variation is inevitable in any process, in any system. So we looked at this regression equation. So there we had mentioned this as a transformation equation. So transformation equation is nothing but our regression equation. So y is equal to f of x plus epsilon. So epsilon here would denote common cause variation. So this is how we would build the regression model. Say for example, you have the two variables as experience levels of the associates and the average processing time. So how will you build the regression model? So average processing time is the y variable. So the regression equation will be average processing time is equal to a certain coefficient value for the experience levels of the associates, right? Say certain coefficient value multiplied by experience levels of the associates plus the constant value. That constant value would indicate common cause variation, which is denoted by epsilon in this regression equation. Clear? So this is how the format is going to look like when we come up with the regression model. So this is exactly what we are going to derive on the 11th day when we perform the regression analysis for that exercise, right? That we saw just now. We also created the scatter plot for that scenario, right? So for that scenario, we'll not only, calculate the correlation coefficient value, but we will also derive this regression equation, right? Now, how to find out that this regression model is a valid one, is the best fit, right? So that is the appropriate term, is the best fit. So there is a metric, right, which would help us to validate whether the regression equation or the regression model is a best fit. And that metric is called as regression coefficient. So just like correlation coefficient, we have regression coefficient, which would help us to understand whether the regression model or the regression equation is a best fit. And this regression coefficient is denoted by capital R square. Regression coefficient is denoted by capital R square. And what is the criteria? So it should be ideally greater than 0.85 or 85%. So regression coefficient should be ideally greater than 0.85 or 85%. But we need to understand for a practical scenario, the regression coefficient cannot be exactly equal to 100%. So for a practical scenario, the regression coefficient cannot be exactly equal to 100%. Why? If the regression coefficient is going to be exactly equal to 100%, then the common cause variation will be 0%, which cannot happen in a practical scenario. We all know that, right? So if the regression coefficient is going to be exactly 100%, we need to understand that the common cause variation for that scenario will become 0%, which can never happen in a practical situation, right? We all need to understand this. So we'll always try to, ensure that the R square value, the regression coefficient value is closer to 100%. So that will be our aim. But we need to understand at any given point of time, we cannot achieve exactly 100% as regression coefficient value, right? So if you say that the regression coefficient value is 100%, it would mean that the common cause variation is 0%, and this cannot happen in a practical scenario, right? But the regression coefficient obviously should be greater than 0.85 or 85% for us to infer that the model is best fit, right? As we discussed just now, the regression coefficient value, R square value, cannot be exactly equal to 100%. So if the R square value is exactly equal to 100%, it would mean that the common cause variation is 0%, which can never happen in a practical situation. But then what does this R square value actually indicate? That is very important, right? Because you can get a question pertaining to this in the final assessment. So what does this R square value actually indicate, right? Say for example, if the R square value is 0.9 or 90%, so what does this actually indicate? So it means that 90% of the total variation that we observe in this Y data set has been explained or contributed by the X variable. So when I say R square is 0.9 or 90%, what does this actually indicate? So it indicates that 90% of the total variation that we would observe in this average processing time data set has been explained by this X variable, which is experience levels of the associates. And 10% of the variation that we observe in this average processing time data set is what we would call as the unexplained variation. And this unexplained variation is what we would refer as common cause variation, and it will be quantified as epsilon in that regression model. So we cannot have a scenario wherein 100% of the variation that we observe in the Y data set has been explained or contributed by the X variable. So this kind of a scenario will never exist, right? In a practical world, right? We need to understand that, right? So we cannot have a scenario wherein 100% of the variation that we observe for this average processing time has been contributed by the experience levels of the associates. So that can never happen. So you'll have only a certain portion of the variation contributed by the X variable. So that will be indicated by the R square value. So R square is 0.9. We will say 90% of the total variation pertaining to this Y data set has been explained or contributed by the X variable. And the balance 10% is what we would regard as common cause variation. And that is quantified and expressed as epsilon in the regression equation, right? Now you can understand how this epsilon can never be equal to 0 in a practical situation, right? So it can be closer to 0, but it cannot be exactly equal to 0. So as the R square increases, you will see a decrease in the epsilon value, right? So as the R square keeps increasing, so it goes up from 0.85 to 0.9 to 0.95, etc. So you'll see a decrease in the common cause variation metric value, which is denoted by epsilon, right? So this is how, we will actually improve the scenario. So we can definitely look out for some more additional excess. So if the R square value is very low, say for example, the R square value says less than 85%. If it is greater than 85%, then it's fine, right? We can infer that the model is best fit. That means, the variation contributed by the X variable is quite sufficient, right? But then if you find the R square value to be 75% or 0.75, so what we can incur through this? So one thing is the X variable that we have considered could be a significant variable for the Y variable, right? But what we need to infer when the R square value works out to less than 0.85 or 85%, so we need to incur or we need to infer that there are some additional X's which we have not considered in the model building exercise. So it's not only the experience levels of the associates, probably there are some additional cost variables which we have missed out considering in the model building exercise, right? So that is the inference we can come up with. So we all know that experience levels have a significant influence on the average processing time. But then if you find the regression coefficient value to be less than 0.85, if it is greater than 0.85, absolutely good. But then if it is less than 0.85, and you also know that the experience levels of the associates have a very strong influence on the average processing time. So what we need to infer here, we need to infer probably we are missing out considering some additional excess in the model building exercise, which we need to do so in order to improve the R square value, the regression coefficient value, right? So we'll also calculate the regression coefficient for this scenario. So we will build a model in the format average processing time is equal to a coefficient value for the x variable multiplied by the experience levels of the associates plus constant. That constant will be the common cause variation, which is the epsilon value, right? And for this regression equation, we will also ascertain what is the regression coefficient value or the R square value. Fine. So as I said, when the R square value is 0.9 or 90%, it means that 90% of the total variation in the y variable has been explained or contributed by the x variable. And 10% variation in the y data set is the unexplained variation. And this is what we will refer as common cause variation. And it will be quantified and represented as epsilon in that regression equation. So that's why I told you epsilon can never be equal to 0 in the practical situation. So with this, we actually come to the end of the analyze phase, right? So this is the end of the analyze phase as far as the common curriculum is concerned. Common green belt and black belt curriculum is concerned. So for attempting the green belt assessment, so whatever we have discussed in the analyze phase is more than sufficient. So as I told you, the black belt specific curriculum will be dealt with on the 11th and 12th day of this training session, right? But as far as the common curriculum is concerned, so it is enough for you to attempt the green belt final assessment, right? But then why are we saying that all these are common curriculum? Because you can also get questions pertaining to these concepts in the black belt final assessment as well. So it is not as if whatever we are going to look at on the 11th and 12th day of this training session, the questions pertaining to those concepts alone will be part of your black belt final assessment. Not like that. You will also get questions pertaining to all these concepts that we are looking at currently in the black belt final assessment as well. So there will be a question on identifying the outlier limit on the upper side. There will be a question on RTY calculation. There will be a question on CP-CPK calculation. There will be a question on yield percentage calculation for a normal scenario. So whatever concepts you have already seen, this common curriculum, you can get questions pertaining to these concepts in the black belt final assessment as well. And apart from that, you will also be asked with regard to the concepts that we are going to see on the 11th and 12th day of this training session. But then 11th day, majority of the exercises that we are going to see will not be asked as questions in the black belt final assessment. But on the 12th day, yes, there could be multiple questions. DOE that we are going to look at on the 12th day, it's a very important concept under the improve phase. And this is a black belt specific concept. And we are going to discuss about DOE on the 12th day of this training session, on the final day. Fine. So this is about the analyze phase. We'll do a quick revision of the analyze phase before we move on to the improve phase, right? So analyze phase, as you would remember, we started with brainstorming for causes because during the define and measure phase, our focus would have been completely on the Y metric, right? Or the CTQ metric or the business problem. And we would have arrived at the baseline performance of the CTQ metric at the end of the measure phase. And we would have also arrived at the baseline sigma level. Only in the analyze phase will be shifting our focus towards identification of causes and root causes. And hence, we will start with the brainstorming for causes. So there are certain guidelines that we are supposed to follow while conducting the brainstorming session. So the people whom you would invite for the brainstorming session, so we should not be looking at their levels in the organization hierarchy. So the only criteria is they should be closely connected with the process, can effectively contribute during the brainstorming session. Another important thing is we should give equal opportunities to each and every participating team member, irrespective of their levels in the organization hierarchy. And there should not be any debates or discussions during a brainstorming session. And no one's contribution should be criticized. And finally, the brainstorming session should be conducted within a limited time frame. So maximum it should not exceed more than 30 minutes. So it should be conducted within a limited time frame. And then once we have conducted the brainstorming session and generated all probable causes, we would then discuss with the subject matter experts and then filter out all those causes that are not relevant to the business problem, number one, and those causes which are duplicate causes. And once that is done, we will construct what is called as cause and effect diagram in order to pictorially categorize the identified causes under 6 category headers. So this cause and effect diagram is invented by Kaoru Ishikawa, and hence this is also called as Ishikawa diagram. And since the category headers will have the names starting with M, so this will also be called as 6M diagram or CE diagram, which is cause and effect diagram, etc. So the 6 common categories or standard categories will be man, machine, method, material, measurement, and mother nature. So mother nature is nothing but the environmental related causes. So once we have the causes identified, we would place all these causes under appropriate categories. So we are free to choose our own category header names, but then it is generally believed that if you are identifying a cause, it would fit into one of these 6 categories. So once the causes are grouped under various categories in a cause and effect diagram, we would ensure that we identify the root cause for a given high level cause by performing 5 why analysis or root cause analysis. So 5 why analysis is all about asking why multiple times, and it is generally believed that we will be able to arrive at the root cause exactly after the fifth why. But there is no hard and fast rule that we need to arrive at the root cause after the fifth why. You would be able to arrive at the root cause after the second why or even after the 15th why, right? And then another important thing to be noted here is we need to conduct this 5 why analysis exercise with the concerned team member or with the concerned team which has actually contributed to the business problem. Only then we will be able to identify the correct root cause for the business problem. And once that is done, we will have a set of 25 to 30 causes. And we know very well that not all these causes will have the same amount of impact on the business problem. So there could be few causes which might have a higher impact on the business problem. The next step would be to identify these vital few causes which might have a higher impact on the business problem. And we are going to use the prioritization tools in order to identify the vital few causes. The first prioritization tool that we saw was Pareto analysis, which is based on the Pareto principle or the 80-20 principle, which says that 20% of the causes identified might have an impact on 80% of the overall problem. Meaning, if you are able to attack 20% of the vital few causes, then we will be able to solve 80% of the overall problem. But then the drawback with Pareto analysis is that we need to ensure all the causes listed have the same unit of measure. That is, the causes should be measured in terms of number of occurrences or in terms of time or in terms of cost, etc. but then the causes have varied units of measure, then we cannot perform Pareto analysis. Then we need to perform control impact matrix or subject to multi-voting exercise. So in case of control impact matrix, we will create a quadrant with control on one side and impact on the other side. So the categories for control will be in control and out of control. Similarly, for impact, it will be high impact and low impact. So in control and high impact causes. So the causes will be placed in appropriate quadrant. So in control and high impact causes will be prioritized first. In control and low impact causes will be prioritized second. Out of control and high impact causes will be prioritized third. Out of control and low impact causes will not be considered at all. Then we have subjective multi-voting, which is all about asking the team members to rate the listed causes in the scale of 1 to 5, 1 being the causes most significant to the business problem, and or sorry, 1 being the causes least significant to the business problem, and 5 being the causes most significant to the business problem. So once the rating scores are provided by the team for the list of causes, then the project lead would collate the information and will arrive at the cumulative rating score for each and every cause in the list. And then he will stack rank them, meaning the cause with the highest cumulative rating score will be placed at the top, and the cause with the least cumulative rating score will be placed at the bottom. And then the project lead can decide that the first 5 or 6 ranked causes can be considered as vital few causes. Now, these vital few causes have to be validated with the help of data with regard to their significance to the business problem. And for this, we'll be using a tool called testing of hypothesis. So since testing of hypothesis is a tool which would actually help us to analyze the sample data and make an inference about the entire population, we also learned about the basic sampling concepts. And we understood that samples will be a subset of the entire population or part of the entire population. But then, since we are going to analyze the sample data and make an inference about the entire population, we need to ensure that the samples are true and fair representation of the entire population. So how to ensure that samples are true and fair representation of the entire population? We need to pick the samples using the correct methodology, number one. And number two, we also need to determine the appropriate sample size by considering the historical performance of the process. Now, 3 commonly used sampling methodologies. Number one, the simple random sampling, which can be applied if the population is homogeneous. That means all the units in the population have similar characteristics. But then, if you have multiple groups or multiple categories existing in the process, then we need to use stratified random sampling methodology. So when we apply stratified random sampling methodology, so we need to first and foremost identify the number of groups or the multiple categories existing in the population. And then we need to calculate the percentage contribution of each of these categories to the overall population size. And once that is done, we will determine the overall sample size, and then we will apportion the sample size to these multiple categories based on their percentage contribution to the overall population size. And once the sample size is known for these multiple categories, I will pick the samples from the specific population category lot in a random way. So hence it is called as stratified random sampling. And the third methodology that we saw was systematic sampling, where the samples will be picked following a structure, following a system. So systematic sampling can be adopted only when we have a sequential production taking place. That is, the production taking place one after another. so that we are able to clearly identify which unit is coming out first, which unit is coming out second and third and so on. So in case of systematic sampling, we would predefine that every nth item coming out of the processing or the production queue will be picked as a sample. So if you predefine that every third item coming out of the production queue will be picked as a sample, then the samples will be picked in multiples of 3. The third item, the sixth item, the ninth item, the 12th item, the 15th item, and so on, right? Multiples of 5, then fifth item, the 10th item, the 15th item, 20th item, and so on, right? So this is systematic sampling. And then we looked at how to determine the appropriate sample size by considering the historical performance of the process. So if you're dealing with a continuous data scenario, then the historical performance metric will be given in terms of standard deviation. But then if you are dealing with binary discrete scenario, the historical performance metric will be given in terms of defective rate. So I told you that we'll get multiple questions pertaining to continuous data sample size determination as well as discrete data sample size determination. So apart from this, you'll also get a scenario wherein the historical performance will not be known to you because it is a new process and you'll be provided only with the confidence level and the confidence interval, and you'll be asked to determine the appropriate sample size. So for that also, I have given the template in the sample size sheet, the exercise file. And once that is done, then we can, perform this testing of hypothesis exercise. So testing of hypothesis, as I told you, would deal with sample data to make an inference about the entire population. But then if you have the entire population data with you, then there is no need for us to perform testing of hypothesis. Because when I say hypothesis, it means making an assumption about the population characteristic. And there are two hypothesis statements that we would frame. Null hypothesis denoted by H naught, which will always take the status quo or equal to position. Alternate hypothesis denoted by HA will be a challenging statement for the null, which is supposed to be proved. So all the decisions in hypothesis testing will be taken from a null hypothesis perspective. So we will either accept or reject the null hypothesis. So if you happen to reject the null hypothesis, there is no other option but to accept the alternate hypothesis. Then we looked at how to frame the hypothesis statements for some 3 scenarios. So specifically, if it is an inspection scenario, so what will be the null and alternate hypothesis statements? If it is quality inspection scenario, the null hypothesis will always be the sample unit is non-defective. And the alternate hypothesis, which the quality inspector needs to establish, will be the sample unit is defective, right? And we also looked at a couple of sampling errors which would be associated with the testing of hypothesis exercise. So the two types of sampling errors, alpha error or type 1 error, which is about rejecting the null hypothesis when it is true. And then beta error or type 2 error, which is about accepting the null hypothesis when it is false, right? And then we also looked at the implication of these sampling errors with respect to all the 3 scenarios for which we frame the hypothesis statements. But then if alpha error is going to be committed in that quality inspection exercise, what will happen? So alpha error or type 1 error is all about rejecting null when it is actually true. So the sample unit is non-defective is a true statement, but then we are going to reject it and say that the sample unit is defective. So a non-defective sample unit will be finalized as defective. So that would be the implication of alpha error or type 1 error. If beta error or type 2 error is committed, then what will happen? So it will be exactly the opposite. Accepting the null hypothesis when it is false. The sample unit is non-defective is a false statement. The sample unit is actually defective. But then we are going to accept the null hypothesis and say that the sample unit is non-defective. Whereas the factual thing is the sample unit is defective. So a defective sample unit will be finalized as non-defective. So that would be the implication of beta error or type 2 error. So you'll get multiple questions pertaining to this, the final assessment. So that is why kind of revise this once again. And then extending this to a manufacturing scenario, the alpha error will also be referred as producer risk, which is about rejecting a good lot. And beta error will be referred as consumer risk, which is about accepting a bad lot. And then we looked at the confidence level and confidence interval. So confidence level, so when we deal with sample data and make an inference about the entire population, we cannot be 100% confident about the population result. So we can be 100% confident only when we measure each and every unit in the population. Otherwise, we can be either 90% or 95% or 99% confident about the population result. But then nothing specific is mentioned about the confidence level. We need to consider the default confidence level to be 95%. So if it is 95% confidence level, it means that we are 95% confident that the null hypothesis statement is valid and 5% chances are there that the null hypothesis statement is invalid and we will accept the alternate hypothesis. Then we also looked at confidence interval or margin of error. Again, when we deal with sample data and make an inference about the entire population, we cannot come up with a point estimate about the population result. We can only come up with an interval estimate. And this interval estimate will be derived at a particular confidence level. So if the confidence level increases, the width of the confidence interval will also become much more wider. And then we looked at the various population and sample notations for the statistical matrices. So mean, it will be x bar as the sample notation and mu as the population notation. Variance, the sample notation will be small s square and the population notation will be sigma square. Standard deviation, the sample notation will be small s and the population notation will be sigma. And then proportion, the sample notation will be small p, population notation will be capital P. Average of a count discrete data, the sample notation will be small lambda and the population notation will be big lambda. If it is size, sample size will be small n, population size will be capital N, right? So why we actually learned all these population notations for the various statistical matrices? Because in the hypothesis statements, we need to incorporate the population notation for a given statistical metric, right? So that is why we need to be aware of the population notations for all these statistical matrices. And then we looked at the list of hypothesis tests. So test for mean, we will have one sample Z or T test. So here the samples will be drawn from a single population category and we would want to validate whether population mean is equal to some target value. But then there are two tests, Z test and T test. Population standard deviation is known. We will apply Z test. Sample standard deviation alone is known. We will apply T test. But then if the sample size is greater than 30, we can apply either Z or T test. And then we have two samples Z or T test. Here the samples will be drawn from two different population categories and we would want to compare the population means of these two categories. And then we have pair T test, which is about comparing the population means of two different scenarios existing in a process. Say, for example, pre-automation scenario and post-automation scenario. And finally, ANOVA, which is analysis of variance. And if you want to compare the population means of more than two population categories, then we need to apply ANOVA. So we also looked at the hypothesis tests under median. So mean as a statistical metric will be applied if the data distribution is normal and random, whereas median as a statistical metric will be applied if the data distribution is non-normal and non-random, right? And these median tests are also referred as non-parametric tests. So all the other hypothesis tests in the list will be called as parametric tests. The median tests alone will be referred as non-parametric tests. So under median, we have one sample signed rank test, which is the equivalent median test for one sample mean test. Mann-Whitney test is the equivalent median test for two sample mean test, and then the Kruskal-Wallis test and Moore's median test are the equivalent median tests for ANOVA. And then we looked at variance, which again needs to be considered only if the data distribution is normal. So we have one sample variance test, which is also called as chi-square test. So here again, we would be validating whether the population variance of a single population category is equal to some target value. And then we have two sample variance test, which is also called as F test, wherein we would be comparing the population variances of two population categories. And finally, we have Bartlett's test, wherein we would compare the population variances of more than two population categories. And then under proportion, we have one proportion test and two proportion test, and one proportion test to be applied if you want to validate whether the population proportion of a single category is equal to some target value. But then if you want to compare the population proportions of two population categories, then we need to perform two proportion tests. Similarly, we have average as count discrete data. So the first test is one sample Poisson rate test, which we would apply if you want to validate whether the average of a count discrete event is equal to some target value. Then we have two sample Poisson rate test, which would be applied if we want to compare the average of a count discrete event pertaining to two population categories. And then finally, we looked at chi-square contingency table, which is also called as test for dependency. So here we would be validating whether the y variable in the case scenario is dependent on the x variable or not, right? And then we looked at what exactly is p-value. So p-value, the full form is probability value. So it is the probability of accepting the null hypothesis. So what is the criteria that we need to apply? So p-value is greater than 0.05 for 95% confidence level. So this 0.05 we could understand is not a blanket criteria. This is applicable only if the confidence level is 95%. So since the default confidence level will be considered as 95%, for majority of the case scenarios, we would end up applying the criteria as 0.05 for p-value. But then p-value is less than 0.05 for 95% confidence level, we will reject the null hypothesis and accept the alternate hypothesis. So for 90% confidence level, the criteria for p-value would change to 0.1 or 10%. For 99% confidence level, the criteria for p-value would change to 0.01 or 1%. So if you can remember the slogan, P low null go and P high null fly, we will be able to take the appropriate decision by looking at the p-value. But as I told you, if you are using my template, even that final inference would be displayed by this template, whether we need to accept the null hypothesis or reject the null hypothesis. And then we looked at the relationship establishing tools like scatter plot, correlation analysis, and regression analysis. So scatter plot, we can get three formation of data points. So when we plot the data points for x and y variables, and if you observe an upward slope like formation of data points, we can infer that the two variables are positively correlated, meaning an increase in the x variable would result in increase in the y variable as well, and vice versa. And then if you observe a downward slope like formation of data points, we can say that x and y are negatively correlated, meaning an increase in the x variable would result in decrease in the y variable and vice versa. But then if you find random plotting of data points in a scatter plot, then we can infer that there is no relationship existing between the two variables. Then if you want to objectively measure the strength of the linear relationship between any two variables, then we need to perform correlation analysis. So in a correlation analysis, we'll be deriving a metric called correlation coefficient denoted by small r, and small r can take any value between -1 and +1. So small r is greater than plus 0.85. We need to infer that there is a strong positive correlation existing between the two variables. If it is between plus 0.5 and plus 0.85, we need to infer that there is a weak positive correlation existing between the two variables. If it is between plus 0.5 and minus 0.5, we need to infer that there is no correlation existing between the two variables. If it is between minus 0.5 and minus 0.85, then we will infer that there is a weak negative correlation existing between the two variables. Finally, if it is less than minus 0.85, we will infer that there is a strong negative correlation existing between the two variables. And finally, the analyze phase, we looked at the regression analysis. Again, both correlation and regression would help us to estimate the relationship between cause and effect. In case of regression analysis, we will be able to depict the relationship through an equation called regression equation in the format y is equal to f of x plus epsilon. So y stands for effect, x stands for cause, and epsilon stands for common cause variation. So the fitness of this regression equation or regression model can be ascertained through a metric called regression coefficient denoted by capital R square. But then the capital R square or the regression coefficient should be ideally greater than 0.85 or 85% for us to infer that the regression model is best fit, right? But then we need to understand that the regression coefficient value cannot be exactly equal to 100%. So if we find the regression coefficient value to be exactly equal to 100%, then we need to understand that the common cause variation will be 0%, which can never happen in a practical scenario. So what does this R square value actually indicate? So if I'm going to say that R square is 0.9 or 90%, it means that 90% of the total variation observed in the Y data set has been explained or contributed by the X variable. So the balance 10% of the variation in the Y data set is what we would refer as unexplained variation. And this unexplained variation is what we would call as common cause variation, right? So this is exactly what we would try to reduce as part of the Six Sigma initiative. So let us have a 15-minute break now. So when we come back, we will look at the improve phase deliverables and also look at couple of tools under improve phase. And then we will have the mock test conducted for the green belt assessment during the final 30 minutes of today's session, right? So now we will have a 15-minute break. Hello, friends. I'm back. Hope you're all back as well. So let us continue. Fine. So just completed the analyze phase. And now we are going to step into the fourth phase in the DMAIC approach, which is the improve phase. Right? So at the end of the analyze phase, we would have identified the list of vital few causes, and we would have also validated the significance of these vital few causes with respect to the business problem by performing testing of hypothesis. And we would have also established the relationship between the vital few cause or the vital cause and the business problem by performing scatter plot correlation analysis, and we would have also derived the regression model, the format y is equal to f of x plus epsilon. So in the improve phase, the main idea is to identify the solutions for these vital few causes and then validate the improvement made, whether the solutions are working fine or not. So there are certain deliverables which we need to adhere as part of the improve phase. So improve phase, we would again start with the brainstorming for solutions. So the analyze phase, we started with brainstorming for causes. So in the improve phase, we would start with brainstorming for solutions. So we will generate alternate solutions for the prioritized causes. So we'll not come up with just one solution for each and every prioritized cause. So we will generate alternate solutions for these prioritized causes, because if the primary solution doesn't work, then we will always have the backup solution available to implement. So if you are identifying only one solution for each and every prioritized cause, then if that primary solution is not going to work, then we need to probably conduct a brainstorming session once again to identify the backup solution. So which will be a time consuming exercise. So when we conduct the brainstorming session, we will identify alternate solutions for each and every vital cause. And then we will categorize all these solutions using this affinity diagram. So there could be different categories of solutions, right? So solutions which would require manual intervention, solutions that would require automation, solutions that would require customer support. So there would be different categories of solutions. So these categories will be depicted in a pictorial format called affinity diagram. And then we will prioritize implementation of these solutions using few matrix or effort versus benefit matrix. So we would have generated alternate solutions for each and every prioritized cause. Now we need to identify which of these solutions I need to implement first. I need to try out first. So for that, I'm going to use Q matrix or effort versus benefit matrix. And then I will also identify the pilot area in the process for implementing the solutions. So I would not know whether a particular solution is going to work out for me or not. So instead of taking a risk by implementing the solutions covering the entire process area, I will actually identify a small area within the process, which will be called as the pilot area, and then implement all the identified solutions. And then we will calculate the improved performance of the CTQ metric, and we will also validate whether we have attained the project goal or not. Remember, the project charter, we would have mentioned about the project goal. So the project goal would have been fixed as per the CTQ metric. So we would validate whether we have been able to attain that project goal or not. And we will also validate the improvement made. So we will compare the baseline scenario with the improved scenario. So if you are talking about comparison of two population means, like the baseline mean and the improved mean, we will perform a PAT-T test. But then if you are going to compare the accuracy percentage pertaining to the baseline scenario with the accuracy percentage pertaining to the improved scenario, then we will perform two proportion test. Or if you want to compare the average productivity pertaining to the baseline scenario with the average productivity pertaining to the improved scenario, then we will perform two sample Poisson rate test. So depending on the metric that we are comparing. So we will use the relevant hypothesis test for validating the improvement made, right? And we will also calculate the improved process capability. So we have already seen, right, as part of the measure phase. So if it is a discrete data, so we will calculate DPU, DPO, DPMO, and sigma level. If it is a continuous data which is normal, we will calculate CP, CPK, and sigma level. And then we will identify the risks associated with the improved process steps by performing an exercise called FMEA. The full form is failure mode and effect analysis. And once the risks are identified for the improved process steps, we will implement appropriate corrective measures or control measures to mitigate those risks. So FMEA is a very important exercise which we will perform as part of our Six Sigma project. But then this is supposed to be done on a routine basis, not just at the time of working on a Six Sigma exercise, because FMEA generally will help us to identify the risks associated with our process steps that we are currently following, and also the product or service output design, right, that we have, right? So FMEA is a very important exercise, just like MSA can be performed on a routine basis. And once that is done, we will modify the process document and also come up with the to be process flow, right? So you would have identified the improved process steps. So we need to make necessary modifications to the process document. And not only that, we also need to come up with the to be process flow. So as I told you, right, when we discussed about the as is process flow as part of the define phase. So as is process flow is the depiction of the process as it is being executed in the shop floor. And that will be considered for the lean improvement. But the to be process flow is the depiction of the process that is supposed to be executed in the future. So that is why it is called as to be process flow. And this will be my improved process flow, right? And once that is done, the most important thing is we need to train the associates or the employees, right, who are connected with that process on the improved process steps. And we also need to get their buy-in. Very, very, very important. So if the associates or the employees, right, connected with that process are going to execute the process as per the old methodology, then whatever improvement we are able to show will not be sustained over a period of time, right? So it's important for us to ensure that the associates who are connected with that process get or bought in to this idea of the improved process steps, and they start executing the process as per the to be process flow. This is very, very, very important, right? So they will have a lot of questions. They will always, try to challenge you. They will keep asking, what is in it for me? Why should I follow the new process steps, right? Even though you might have simplified the process and would have handed over to them, but they would have got habituated, performing or executing the process as per the old methodology. So the habits cannot die easily. So they will have the tendency to execute the process as per the old methodology. So it will be highly difficult for them to adopt the new methodology, right? Even though it could be a simplified version of the old methodology, right? So they all, would have you got used to touch the nose by taking their hand round about the head, right? The roundabout way. That being the case, you are teaching them to touch the nose directly with their finger. So that would be very difficult for them because they have got habituated by taking their hand round about their head and then touching the nose, right? So hence, we need to understand that it's not going to be easy for them to straight away start executing the process as per the improved process steps. So we obviously need to get their buy-in. So they will have lot of questions to ask, and most importantly they will always try to find out what is in it for them, so why they should actually follow as per the improved process steps. So we need to definitely spend some time, explain to them, convince them that the new process steps can bring certain benefits to them. And once we get their buy-in, then they will be sincere in executing the process as per the improved process steps. But without getting their buy-in, if you're simply going to orient them, not bothered about whether they are interested in executing the process as per the new methodology, then there is every chance that the associates connected with the process would continue to execute the process as per the old methodology. And in that case, you will not be able to see a sustenance in the improvement made, right? It's important for us to ensure that the associates are oriented on the new process steps and also they are bought into this idea. It's very, very important. And once we do that, we can always scale up the solutions covering the entire process. So these are the various steps that we need to follow as part of the improve phase. And most of the tools that we see in the improve phase, we have already seen it in the earlier phases. Say brainstorming, we have already seen. Affinity diagram, we already looked at as part of the define phase. Again, process capability analysis, we have already seen, right? So the process flow, we already seen. So most of the tools that are listed here, we already looked at as part of the earlier phases. But as part of the improve phase, we are going to look at Pew matrix, effort versus benefit matrix, and of course, failure mode and effort analysis, which is FMEA, right? The FMEA exercise is something that we will see in detail, right? So how this exercise needs to be conducted and how we need to update the information in a standard template, right? It's a very important exercise. And then as part of the black belt specific curriculum, we are going to look at a very special concept under improve phase called design of excellence. In short, it is referred as DOE, right? So these are the various tools that we'll be looking at as part of the improve phase. So first we will look at the Pew matrix, right? So Pew matrix, as we just now discussed, is the tool that we will use for prioritizing the solution. So you'd have generated alternate solutions for each and every priority cost. So which solution I need to implement first is what I need to decide using this Pew matrix and effort versus benefit matrix. So first we look at the Pew matrix. So Pew matrix, first and foremost, we need to identify the criteria elements for implementing solutions. So what are all the criteria elements that you would consider for implementing the solutions, right? So as far as I am concerned, I will definitely look at the cost effectiveness, whether the identified solutions are cost effective. That is number one. And number two, I will also look at the timelines for implementing the solution, how quickly the solution can be implemented, right? And the third one is the replicability, whether these solutions can be replicated in a similar process, right? So these are the three criteria elements that I will consider for implementing the solutions. But you can have your own list of criteria elements. So there is no hard and fast rule that we need to consider only these three criteria elements. But then we need to ensure that the list is short and crisp because we need to provide weightage for each and every criteria element based on the importance that we wish to give them, right? So based on the importance we plan to provide for these criteria elements, we will come up with the corresponding weightage. So for me, cost effectiveness is very, very important, right? So I am giving a weightage of 50% for cost effectiveness. In terms of decimals, it will be 0.5, right? And for me, the next important criteria will be the timeline for implementing the solution. So I'm giving 30% weightage for that. And then the third one obviously will be replicability, wherein I will give the balance 20% weightage for replicability. So once I have assigned the weightage for each and every criteria element, I will then rate all the identified solutions against each of these criteria elements in the scale of 1 to 5. 1 being the criteria element is least favorable to that particular solution, and 5 being the criteria element is most favorable for that particular solution, right? So, for example, solution 1, if I'm going to provide 5 as the rating for cost effectiveness, it would mean that the solution 1 is very, very cheap. Or if I'm going to give, rating 5 for timelines, that means that the solution 1 can be implemented quickly without any delay. Or if I'm going to give 5 as the rating for replicability, it means this solution can be replicated in a similar process area without any challenge, right? So this is the meaning of rating 5. Similarly, rating 1 means the solution is very, very costly. Then I'll give rating as 1 for cost effectiveness. Rating of 1 for timelines will be this solution is likely to take a longer duration for implementation, and rating of 1 for replicability would mean that this solution is very, very rigid. It cannot be replicated in a similar process, right? So that's the meaning. So in the scale of 1 to 5, I will provide rating for all these solutions against each of these criteria elements. So once the rating scores are provided for the multiple solutions that I would have identified for a priority cost, I will calculate what is called the total weighted score. So how this total weighted score will be calculated? So I will simply multiply the rating I have given for a particular criteria element for a given solution with the corresponding weightage. So for solution 1, if I'm going to calculate the total weighted score, it will be 3 multiplied by 0.5 plus 4 multiplied by 0.3 plus 2 multiplied by 0.2. So once I multiply the rating that I had given for a particular solution against each of these criteria elements with the corresponding weightage and then sum it up, I will get the total weighted score. And once this total weighted score is arrived for all the multiple solutions, I will find out which solution has the highest total weighted score, and that solution will be prioritized for implementation, right? So this is how I will perform this Pew matrix exercise. Again, a very, very, very easy quality tool, and this can be used even for taking some personal decisions. Say, for example, you have plenty of options to visit a restaurant and you're totally confused which one to visit. So you can perform this Pew matrix exercise, right? So you can finalize on the criteria elements you would consider for visiting a restaurant, and then you can assign weightage for each of these criteria elements based on the importance you plan to provide to them. And then we will have the restaurant names in each and every column. And then we will provide a rating in the scale of 1 to 5 for all these restaurants against each of the criteria element. And then we'll calculate the total weighted score and find out which restaurant has the highest total weighted score. So that restaurant will be prioritized for the visit. Or if you are confused with regard to identifying a vacation spot, we can perform the Pew matrix, right? So this, particular exercise can even be performed for taking some personal decision, right? That's why I told you, majority of the quality tools, if you see, can also be applied in our day-to-day personal lives, not only in work-related scenarios, but also in our day-to-day personal lives. So another tool that would help us to prioritize implementation of solutions is effort versus benefit matrix, right? So this is similar to our control impact matrix. So control impact matrix will be used for prioritizing the causes, but effort versus benefit matrix will be used for prioritizing the solution, right? So what we will do, we will again construct a quadrant. So one side of the quadrant, we will have the effort, and the other side of the quadrant, we will have the benefit. So effort and benefit. So the effort will be low effort and high effort. Similarly, benefit will be high benefit and low benefit, right? So we will place the identified solution in all these quadrants, the appropriate quadrant, and which one you will prioritize. So obviously low effort and high benefit will be prioritized first. Low effort and low benefit will be prioritized second. High effort and high benefit will be prioritized third. And the final one, high effort and low benefit, is something I will not even consider. So this will be my order of priority when I place the solutions in the appropriate quadrant in this effort versus benefit matrix. Again, a very, very simple tool and a subjective tool for prioritizing the solutions, right? So this is how we would prioritize the solutions that we need to implement first. So when we have alternate solutions identified for a prioritized cause. So once that is done, then we also need to identify the risks associated with all these improved process steps. And for that, as I told you, we will be performing this exercise called FMEA. The full form is failure mode and effect analysis. So since this is an important exercise, so we will look at it fresh tomorrow evening, right? So let us stop here. So now we will have the mock test conducted for green belt assessment. So if you have any questions, you can ask me now. Any question? Right. So those who want to take the mock test now can actually stay online and then take the mock test. So I will also remain online for the next 30 minutes or so, right till the end of the mock test exercise. And in case of any clarifications, you can always connect with me and then ask me the question. But then if you decide to take the mock test at a later point of time, you can do so. So the correct answer for the green belt mock test questions will be shared with you tomorrow morning through the common WhatsApp group. So you can always validate whether you have answered a particular question correctly or not. So in case of any clarifications, you can always connect with me even during the daytime, as I told you on the very first day, right? And those who are directly enrolled for the black belt certification program, and as I told, they will not be eligible to take the green belt mock test or the green belt final assessment. And if they want, they can exit and then join for the 10th day's training session tomorrow evening at the same time, right? So those who are taking now, so can attempt the green belt mock test. So let me just send the procedure for accessing the test link. So the test link needs to be accessed only through the portal, only through the IMC portal. So that's why I told you last week itself that we need to uh, use the user ID and password credentials for logging into the IMC portal. And this user ID and password would have been already sent to you, right, through email before the start of the training program. So you must be having that. So you would have also logged in and then you would have looked at your dashboard, right? So you would have also verified whether you have been enrolled for both green belt and black belt certification programs. But then if you have been given exemption, as I told you, you can directly take the black belt mock test and the black belt final assessment. But anyway, I will send the procedure for accessing the test links. Just give me a second. So I have sent the procedure for accessing the test link through the common WhatsApp group. I will now send the updated files as well so that you can simply download them and then start attempting the mock test for Greenbelt assessment. Just a minute. I have sent both the updated files, the notes and the exercise file. So you can download both the files in your system and you can start answering the mock test questions. Right? So tomorrow we will cover the rest of the portions, the improve phase, wherein we are going to look at FMEA, and we will quickly look at the control phase deliverables as well. And then we will have a discussion on the project exercise. So I will take you through the sample project document and also the project documentation template. And I will also take you through the project initiation form, right, which you are supposed to fill in if you are interested to work on a Six Sigma project exercise after the training sessions are over, right? So I will just give a brief about the project exercise tomorrow. And after that, if time permits, we will do a quick revision of the statistical exercises, right? So all those statistical exercises which might appear as questions in the Greenwell final assessment. So we will probably do a quick revision of the same, and I will also help you understand how to input the values in the template and interpret the answers, right? And we'll also go through the template reference sheet that we have in the statistical exercises file. Fine. So this is going to be the agenda for tomorrow. And the final 60 minutes, tomorrow you'll be taking the Greenbelt final assessment. Fine. So you can proceed with the mock test. So you can start answering the questions. So I will remain online, as I told you. But then in case of any clarifications required, you can always connect with me. So all the very best to each one of you. And those who are directly enrolled for the Black Belt certification program, they can exit now, and we will connect at the same time tomorrow evening for the 10th day session.
Sure. Thank you, Sridhar.
Yeah,
I'd like to
thank
exit.
you. Yeah,
Thank you.
thank you.
Thank you, Sridhar.
Thank you. Another information, even if you pass the mock test, right, you can attempt it 2 more times. So you can get some good practice. It's not as if you'll get a totally different set of questions the subsequent attempts, but at least few of the questions could be different. So you can get some good practice.
So it's done. Can we leave?
Yes, please.
Yeah,
So
thank
we'll
you.
connect tomorrow for the 10th day session. Yeah,
Sure, sir. Thank you.
thank you.
Thank you, Sridhar. Mine is also done.
Thank you.
Yep. Bye-bye.
I have completed too.
Okay, so we'll connect tomorrow for the 10th day session. Thank you.
Thank you. Good night.
Good night. Okay, then. So close the sessions for the day. So we'll connect at the same time tomorrow evening. Thank you.